Hello. Audible, right? Thank you for my introduction. I will introduce myself once again. I'm Dr. Lohit Naik and I'm doing postdoctoral research with Dr. WSG. And I'm very happy to share my knowledge on recent trends and challenges in OLED technology. Um, this is my outline of my presentation, which contains the following things. I will not bore you. It's already 4:15, I know. So I mainly prepared my presentation for UG and PG level students. So I will try to attract you for this field. So, dear student, have you ever seen this device? Yes, you right. So it's a tungsten filament lamp. So which is invented by our scientist Thomas Alva Edison, right? Yes, right? Sir, cheer up. Don't worry. I will not bore you. Okay. So, have you ever seen this device in the future world? That means the present world? No, right? Sometimes, yes, I know. But in some copy or some restaurant to give vintage look, we use this kind of device, right? So, question is why? So, it's very simple. So, if you figure out the answer for this question, definitely you know why I choose this topic for the presentation. Okay, so I list out some important points where actual optoelectronic device must have, right? If I choose tungsten filament lamp, whether it has this kind of properties or not, let's check. So our tungsten filament lamp does not have long lifespan, energy efficiency is very poor, ability to operate in a cold condition is not possible. It emits a high heat, right? Because lot of energy loss in terms of heat. And design flexibility is very poor, and also it can't operate in a low voltage. So these are the some disadvantage of the incandescent bulb, right? So how we can overcome this, right? So see, over the decades our scientists are working on this field of the electronic device and build up following device. You know this. One is tungsten filament lamp, tube light, CFL, and finally LED. And you know how its luminescence efficacy is increased in each stage. So finally, what we found at the end, now present world, we found LED, right? So who is invented this? The famous scientist Nick Kolnick, right? The question is how it works. So once again, I will not go in deeper. I will just tell how it works. Okay. So we know that what is light emitting diode. It's a basically made up of diode, which is a construction of PN junction, right? So how we construct P-type semiconductor or N-type semiconductor? If you construct N-type semiconductor, you just do what? Pentavalent atom to the pure semiconductor so that you can create the holes. And if you generate p-type semiconductor, you can just do trivalent atom so that you can create the hole. Sorry, in pure case it's electron, and in this case it's hole. So how LED works? It's very simple. When your electron and hole recombine and resultingly produce the photons, right? Okay, so this is how LED works. But how it related to the my field, organic light emitting diode? Why I choose that concept for the presentation. So before that, I will choose one example so that you can understand why OLED overrule the present world. So you know this term, right? Liquid crystal display. Okay, and most of the monitor TV or monitors are constructed with the help of LCD, but it is paired in a present era, right? Before that, how it plays, I will explain later, but let's understand how it works. So basically, your LED containing the present layers, like one is backlight, another one is diffuser, then color filter and glass. So we are heard about the pixel, right? So every phone, every display containing the pixel and its resolution. So here you can see this is the pixel. If you turn on the backlight, it will glow the individual pixel so that you will get the white light. Very simple. The question is how it generate the image, right? So if you control the each pixel color, then you can get the image. Then in this section, you can't control the individual color of the pixel. But on introducing the LCD screen or LCD molecule, you can control the pixel luminosity. How? See, your backlight emit the unpolarized light, which is polarized by the diffuser when it passes to the liquid crystal display, and your liquid crystal molecule is what active to the polarized light, so that it will control the RGB color. That means red, green, and blue. Basically, using this color only, you can generate any millions of colors or any possible color. This is the fundamental, right? So you can control the intensity of this pixel so that you can get a different color. For example, here I have intensified the red and green, and blue is low intensified so that we can get the yellow color. Similarly, if you get pink, you can like that. You can modify or control the intensity of the RGB filter. You can get the different color. Now, then how this LCD display failed? That is the question, right? So first of all, it will not produce the perfect black display, right? It is not produce a perfect black display. And also, it containing the many layers like you need backlight, diffuser, LCD screen, then color filter as well as okay glass leave it at both. So can we modify this or can we simplify this? So you can see some monitor which has some certain inches of thickness. Can we minimize that thing? Yes, it is possible, right? So let's uh, try to modify this screen first. How we can change this? That means can we remove the backlight and diffuser? Okay. So answer is yes, we can, right? By modifying the things. Like, I can replace this by LED. Like, if you individually illuminate the each pixel, you don't need of any backlight, right? So you can think that I can place some inorganic LED in place of backlight. But is that really possible? The answer is no. Why? Because LED has certain limitation. What is that? Okay, so these are the some limitations that LED has. One is like a blue hazard, blue pollution for eye safety. Then light quality. That means our LED does not produce the black body radiation spectrum. And also temperature dependency. Like when you increase the temperature, your LED get burst, right? Then also voltage sensitivity. It's a very important factor. So your LED will work above voltage threshold voltage and current should be below rating. So you need some resistance, voltage regulator device and all. And also high initial price, to construct the semiconductor, you need clean room and all. That's why you need some initial capital to start this industry. And also area of the light source, sorry, area light source. That means your LED should not produce any uh, uh, normal light. It will produce the Lambert distributed light. Okay, so these are the some limitations. That's why we can't use the LED as a backlight for the present display. Then question is, if you are not use the inorganic LED as a display, backlight as a LED display, then what is the replacement for that? Then comes into the picture of can we use the organic molecule? Yes, it is possible. Then first time Stephen VK invented organic molecule or a semiconducting organic molecule and successfully construct the OLED. So as I mentioned earlier, we know that how light emitted in the LED, right? When an electron hole combine, then only you can get the photon. But this is the molecule. So here we have a molecular orbital. So you may heard these terms, HOMO and LOMO. Okay, there's a highest occupied molecular energy level and lowest unoccupied molecular energy level. Okay, you due to the electronic takes place from these energy levels, then only you can get the photons. Okay, so is that simple to construct the OLED using this material? Whether we need some kind of engineering on that, yes, you need it. So it's not that easy, but you can even get the better performance than the inorganic LED. So how actually our organic LED look like, or how it constructed? See, this is the thing where we have our OLED. So it containing uh, different parts. So one is cathode, then electron injection layer, electron transport layer, hole blocking layer, MEC layer, electron blocking layer, hole transport layer, hole injection layer, and anode gas substrate. But total thickness of this OLED is in terms of 100 to 150 nanometer. Now you can have the flexibility to compress your display, right? So one one more question: why we need this much of layer to illuminate the light? As I mentioned earlier, if electron hole combine, then only you can get the photons, right? So here also we need electron transport layers and hole transport layer. So you can do your research on any one of them, but I am doing my research on MEC layer. I will tell you why I choose this one. Okay, so this is how your organic LED illuminate the light. Now you have the flexibility. Then okay, so how in which factor we can consider our organic molecule as a good optoelectronic device for present studies or any other application. So it is dependent on these two factors, that is internal quantum efficiency and external quantum efficiency. So internal quantum efficiency is nothing but ratio of number of electron pairs or charge carrier generated to the number of photon absorbed by the active layer. Along with external quantum efficiency is nothing but number of outcoupled photon per injected charge. Okay, these are the two parameters where we can judge whether our constructed OLED is having the good properties or not. Then once we consider the or once we develop this kind of OLED, then we can easily illuminate the individual pixels and we can perfectly get the backlight. But question is, uh, still we can modify this display or still we can compress this display? Yes, you can. So can we, okay, what else we can remove from this display? So we can't remove the backlight. So we can remove the RGB filter, right? So this is the possibility that we have. So, but question is how? Then we can even generate or construct the different light emitting OLEDs. Like, instead of RGB filter, we can even select the red, blue, green emittive organic LED, right? So question is how you achieve that? For that, very simple. You know this is your MEC layer, right? This is your MEC layer. Sorry. Okay, this is your MEC layer where you can dope different molecules, organic molecules, which is specially designed. Then you can tune the color. That means if you tune the band gap, you can get the different color, right? So see, this is how you can. It's not that simple. It's having some procedure, but graphically I am showing like this. Now, so once you dope this material to in your MEC layer, then you can get the different band gap so that you can get the different color. When you combine this, then you can easily produce a good quality of display or good quality of image. Finally, what is the basic necessary condition to uh, explain whether our OLED is performing very well or not? So these are the following points that should OLED have, which can be implemented in the practical device. So one is it should be high thermally morphologically stable, and it should have very high homolumo levels and balanced hole injection, electron injection from both sides of the MEC layer, and a high photoluminescence quantum yield of the MEC layer. This is a very important factor. See, whenever we construct any fluorescence or uh, uh, you know photoelectrical active material, it should have some good quantum yield. Quantum yield is nothing but if your molecule absorbs 100 photons, if it emits 100 photons, then we can say its quantum yield is 1. But practically it is not possible. You know that. Why? Because there is an energy level losses take place in when electron excited to the high energy state. So this is how occurs. That's why. But we have to design such kind of molecule which should show the good quality of quantum yield. Okay. Then Okay, so high enough singlet and triplet level of hole transport layer and electron transport layer and host material to ensure the exciton confinement. These are some in the different layer of the. Then this is the very important you know diagram in this section, because see how our OLEDs growth in each uh, time interval, from the beginning. So see here, our first generation OLED is designed by the fluorescent material, which has a very low efficiency but high lifetime, reasonable lifetime. Okay, no problem. So that means the molecule shows for fluorescence, you can directly use it as a OLED. But later on, it containing its drawbacks. It shows its drawback. That means it shows a very low internal quantum efficiency. So it's up to that 25% show the quantum efficiency. That means maximum energy losses take place. So once energy losses take place, that means you are consuming a lot of power. So next, let's come to the next second generation OLEDs, which is constructed by the phosphorescent material. Okay, these are the some terms, the fluorescent and phosphorescent. Fluorescent is nothing but when electronic transition takes place from the singlet energy state, and your electron should lies in the excited state in the 10 to minus 9 seconds, then you will get the fluorescence. If you get the phosphorescence, then your transition should be take place from the triplet to ground state, and at that time your electrons stay in the excited state in terms of minutes. Okay, so these are the process. Now, if you construct the OLED using the phosphorescent material, you will get the benefit that you will get high efficiency, long lifetime for red and green, not for blue. And these kind of material containing heavy metals, and which is hazardous to us and environment. Okay, so to overcome this, there is one more OLED that is called TTF, that is triplet fluorescence OLED. That means they are what they do, they just mix the fluorescence and phosphorescence OLED and construct the new material. But it shows some moderate efficiency and a reasonable lifetime. Later on, what happened? That is third generation OLED, which is dependent on thermally activated delayed fluorescence material. What happened here? They just reduce the energy gap between triplet and singlet energy levels and achieve the maximum internal quantum efficiency. So in this kind of material shows the high efficiency. They are not use any heavy metal ions, but still lifetime of the blue LED is very short. Still problem is not resolved yet for the blue LED. Next, once again, they are once again doing engineering on the energy levels and build hybrid local and charge transfer state, so that they will get the high transition between the ground to excited state. That means reduction of the energy loss in excited state. So in this case also you will get the high efficiency. Here also they are not using any heavy metal ion, but once again lifetime is of the blue light emitting LED is very low. Now present days, a lot of research is going on the blue LED. The question now you understand, right? Why we are focused on this. Okay, red and blue LEDs are sorry, red and green LEDs are already have sufficient efficiency, but as compared to blue, it has very low efficiency. So why we need this? Because we have to develop the proper display, right? Now, so this is how present day research is going on. Now these are the some materials which is used for electron injection layer, and this is for hole injection layer. And here, see, you can see these are the material over the period they are developed by the scientists for green emission. Okay, which containing some of them containing metal ions, organometallic complex, and some of them are simply organic molecules, and some of them are in polymer also. And this is the material which is used for the red fluorescent, red illumination. And finally, this is for blue. And all this you can see the external quantum efficiency value. Okay, so over the period of time they are increase the quantum external quantum efficiency of the molecule. So finally, question is, once you prepare the molecule, is that only experimental thing? Sorry, by constructing the device only you can know whether your molecule is suitable for the OLEDs or not, or something else technique that we have to characterize those molecules. Yes, you can theoretically estimate the organic molecule properties. How? So here we have the software called Gaussian, okay, where you can estimate the multiple parameter of the molecule like photophysical, uh, photochemical, and even thermodynamical and nonlinear. There are a lot of parameters that you can estimate using this software. Okay, so sorry, one minute. Okay, okay. See, this is the molecule which I draw in the Gaussian software where you can see your molecule in a three-dimensional way. So see, you can uh, design your molecule, or you can see your molecule in a three-dimensional. And along with that, you can even calculate the homology energy levels, right? As I told earlier, if you want to know different, which color light which is emitted by the OLED, you can judge by its energy band gap. So using this software, you can even estimate the HOMO energy level and LUMO energy level, and along with that is electron cloud. See, this is the molecular electrostatic potential map where we can understand how your electron is distributed over the molecule, right? So red indicate the electron uh, what efficiency, and blue indicate the electron acceptor properties. Okay, this software may help you to understand the photophysical parameter of this some organic molecule. Okay, so when I completed my PhD in 2019, then I started my independent research. Then I collaborate my you know one person from Taiwan, and we together synthesis one molecule which is the imidazole based zinc complex, and we are construct the LED and study its performance. So then we found that our LED shows the sky blue color. As a beginner, I found very good result as per me. Okay. So along with that, I estimated its MESP plot and all, and I got some good quantum yield, external quantum yield. But later on, I did, I when I did my literature, then I realized that so this is not the end. So we have to do something else. Like present day problem is what we have to give the perfect blue color LED, right? So then I discuss with okay this result, yeah, I have published in one of the journal that is Chemistry Select. Okay, so then I discuss my ideas with my one of my collaborator who is in Karnataka University, and finally we end up with a very good material which is perfectly emitting the blue light. Okay, so it's a emission near 380 nanometers in perfect blue region. So we are calculated photophysical parameters and biological parameters and published in this paper. Now we are thinking about to construct the deep blue emitting OLED, and its work is in pipeline. Uh, Finally, this is the paper for it's for UG and PG level student who really want to work in this field. You can go with this paper. It containing lot of data how our OLED generate field is actually generated and how it propagated in a different region, and how each stage problem is troubleshooted by the scientist. That all things included in this paper. Finally, uh, see, once you construct the material, definitely, if it has, sorry, it has some advantages, then definitely it has some disadvantages also, right? So till now, okay, till now, OLED has following disadvantages. I don't know in future, but till now it has some disadvantages like reflective light technology is not used in the device. Over time, OLED pixel brightness is decreases. Lifetime of the device is very poor as compared to LCD and LED. Manufacturing process is expensive right now, and water can easily damage the OLED. And red and green LED have the longer lifetime, but blue LED has very shorter lifetime. So these are the things that is in the our OLED. And okay, thank you. So this is the concept. Okay, I can take some few questions. Okay. Actually, that is a very good question, sir. So one thing is we have to select some material by the literature first thing, and second thing, material should have high conjugation. So if you have the larger delocalization, you can get the high fluorescence. Along with that, sir, what happen if your molecule containing the donor acceptor group, like I will show you this uh, MESP plot. See, in our molecule, you can find the two regions, red region and blue region. In internal, what happen? Electron is delocalized from the acceptor to donor. If you increase this kind of structure, then you can get the better performance, sir. Yes, sir. Okay, sir. What happened? This is set by the eye safety organization. Okay, so we are repeatedly working on the display techno. So everyone is nowadays working on the computer, but they don't bother about the blue light emission. It will definitely harm our retinas. So there is certain limitation. That means intensity limitation for that light. So we can't cross that limit. So, but basically LED, what happened due to the improper, engineering or tunability of the structure, it will emit the blue radiations. So which will harm our eyes. So, but you can even minimize that things in OLED. Yes, you can, sir. But in future, we can completely diminish that also. And if I get some question from the PG level student, that's also yes, very good. Huh. Okay. Okay. That's good question actually. See what happened. We know that Vibgyor, right? So we can't produce the ultraviolet light. It's once again harmful to our skin. So you have to set or you have to synthesize such molecule which should emit the radiation in between 350 nanometer to 380 nanometers. So you know if you succeed in synthesis of those kind of material, along with that you have to focus on whether that molecule is thermally stable or not. Okay, that should be also in your mind that whether your molecule is thermally stable or not. Okay. Uh, yes. That means, sir, crystal line. You are asking about that, or structure means can get that. Sorry, I don't know that. Sir. But this molecule. Sorry, sir, I don't know. Sorry, right now I don't know. I will figure out that. Yes. Uh, right now, see, work is still in progress. I'm not telling that our LED OLED is completely well punished right now, but still work is going on. I don't know the actual number how extent, but as compared to the LCD, it will fade up. Sir, sorry. Ye- Yes, sir. Yes, sir. Yes, sir. See, doping effect in okay, sir. Sorry, I didn't. Hmm. Okay, so thing is, if you minimize the band gap, you can get the different colors. So for that, you have to once again do the literature and find some moiety which will decrease or increase its band gap. There definitely it will depend on the doping effect also. Yes, sir. Yes, sir. Uh, no, no, it's a very good question, sir. In number wise, you are asking, or some, you know, so as per the literature, they are telling that if you combine blue, green, red in a proper manner, you will get the perfect black color. So for that, you need the color purity. So what happens, sir? If we have the fluorescence emission, that means we have certain range of the emission spectrum. We can't get a single emission, but we can get the range of the. For example, we can get 450 to 550 nanometer scale of emission. If you compress that emission range, then you can get the color purity, narrow emissions, and some more. Yes, lives. Right now, I don't have the data. I will give you. Okay. Uh, Yes, of course, of course. The in disadvantage, I mentioned that no reflection technique, right? When you read your display in external sunlight, still you know we have not developed that much technology to overcome that. Still progress is going on, but definitely in future, OLED is the major thing that is included in the display technology because you have the ability to tune the emissions and some properties. That is the beauty of organic molecule actually. Yes. Huh? Okay. See, blue light will harm to your eyesight. So international eyesight safety limit, they mention some the intensity range. If you cross that, it will damage your retina. That's why they thought. Okay, blue pollution. So I will tell you. So uh, it is set by international. I will tell you. Sorry, I took the definition of that actually. I have that. Sorry, I will show you in better. Uh, okay, so you can see here. So oh, sorry. Um, Wait a second. I think I missed that. I will let you know. Okay. Um, Definitely. Sorry for that. It's also it comes into safety manners only. Ma'am, no, actually UV light, we are not generating any UV light. UV light. If you eliminate the UV light, it definitely causes the cancer. Huh. Yes, maybe. Of course, maybe, ma'am. Sorry, I will figure out that actually. Yes, I will get the proper answer for that. Okay. Then anything else? Yes. LED. OLED still have that problem. Still, we have to improve that. In terms of number, sorry. Uh, okay. What? Uh, Okay. So first is formation of excitons. Okay. So and improper substitution of the functional group to the organic molecule. So first thing, see what happened in order to eliminate the blue light, you need high energy. Okay. In that case, your molecule should be stable. But as compared to red and green, its band gap is very small, right? You need minimum energy. Okay, in that sense. So, but in future maybe we can find out some new material so that we can get uh, pure good light emitting source, blue light emitting source. Okay. Ah. Okay. Active matrix or organic light emitting diode. No. See, AMOLED is the modified engineering version of the OLED. In that you are using OLED only, but in a proper manner. I don't know right now that I. Huh. No. Organic molecules are the macromolecules. Okay, quantum dots are something else. And anything else? Yes. Delocalization of? Didn't get that. Sorry. Huh. Okay. For that, I'm explaining all about the molecular spectroscopy and vibration energy level, everything. Then only I can easily explain those things. That means in fluorescence, what happen if electron transition take place from the singlet ground to the singlet energy level. See, if I want to explain these things, then I need one more session to complete all those things. But actually, that is a good question. Nouri. In maybe in this semester, maybe you will learn that molecular spectroscopy and all.